convection heat transfer takes place, there is conduction taking place too. Alright, so this is what we're going to be looking for. Okay. That is just a simple thought experiment. And now what we will do is the following. Yes, this question.
So if you're sitting in a pool and there's no real bulk motion, would you treat that interaction with the fluid as conduction?
If you're sitting in a pool, now depends on what is hot and what is cold.
Okay.
Right. Because you see, I can have a situation of this nature here, right? So I do not have a natural convective current created. So that depends on that. But there is always radiation. So even if you're swimming in an ocean and you are very, very far away from somebody, there is still radiation heat transfer. You won't feel it as much though. Alright, now what we want to do is, when we talk about convection, forget the Newton's convective law of cooling that we studied, in its form that we studied. Okay, so we had looked at Q convection as H times A times, T1 minus T2. We had called this character H as the convective heat transfer coefficient. This is Newton's law of cooling. Forget that particular expression, the way it is labeled, we are going to label it in a different manner. And here is what we are going to do. Let me take an airfoil. Okay, and let's say that there is wind blowing past this airfoil. This is the free stream condition, U infinity and T infinity. Let's say that the surface temperature of the airfoil is maintained as Ts. I can apply Newton's law to the entire airfoil, assuming that the surface temperature of the airfoil is greater than the ambient temperature. Here is Newton's law of cooling. Q is H bar, let's say flux, okay, per unit area, H bar times Ts minus T infinity. This is the convective law applied to the entire airfoil. And in this case, H bar is going to be called as the bulk heat transfer coefficient. Okay, so this is H bar is the bulk heat transfer coefficient is HTC from now on. So this is the bulk heat transfer coefficient. I can also do the following. Take a small surface area on the airfoil. Let's say the surface area there is dAs. Okay, so in this case, let's say that maybe I'm not looking at the flux, but the net one is Q is As. As is the total surface area that is available for heat transfer, that is the fluid interacting with the surface of the airfoil. Now the local surface area there is going to be dAs, and what we are going to say is that for each and every small piece of the airfoil, however small you want it to be, I can come up with a local heat transfer coefficient, which is going to be changing at each and every point in the damn thing. Okay, so there is going to be this fellow called a little h without the bar. Forget this formula. Little h is called the local heat transfer coefficient. Varies at each and every point. But I can still write the law of cooling by saying, okay, dq convection over that particular area that I am choosing is going to be h times Ts minus T infinity times dAs. Does this make sense to everybody? I'm applying Newton's law of cooling for that small portion and very last minute. If I integrate all of this over the surface area, then I get Q. So integral dq convection is equal to Q. Factor of Ts minus T infinity is common for both. So this tells me that H bar is 1 by As integral H dAs. Okay, this is just by taking this expression and integrating it over the area and equating it to the expression there. So this is the relationship between the bulk and the local. Thank you very much.